Okay, this is part 3 in Sir Isaac Newton's Mathematical Principles of Natural Philosophy and his System of the World. I'm up to axioms or laws of motion. Okay, law 1. Every body continues in its state of rest or of uniform motion in a right line unless it is compelled to change that state by forces impressed upon it. Projectiles continue in their motions so far as they are not retarded by the resistance of the air or impelled downwards by the force of gravity. A top whose parts by their cohesion are continually drawn aside from rectilinear motions does not cease its rotation otherwise than as it is retarded by the air. The greater bodies of the planets and comets, meeting with less resistance in freer spaces, preserve their motions both progressive and circular for a much longer time. Law 2. There's a portion in italics, and then there's, which I guess represents the actual law, and then there is a paragraph, not in italics, explaining it, or giving an example rather. So for Law 2, the summarized law is the change of motion is proportional to the motive force impressed, and is made in the direction of the right line in which that force is impressed. And then the example is, if any force generates a motion, a double force will generate double the motion, a triple force triple the motion, whether that force be impressed all together and at once, or gradually and successively. And this motion, being always directed the same way with the generating force, if the body moved before, is added to or subtracted from the former motion, according as they directly conspire with, or directly contrary to each other, or obliquely joined when they are oblique, so as to produce a new motion compounded from the determination of both. Law 3. To every action there is always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal and directed to contrary parts. So that's quite a familiar one. The explanation is this. Whatever draws or presses another is as much drawn or pressed by that other. If you press a stone with your finger, the finger is also pressed by the stone. If a horse draws a stone tied to a rope, the horse, if I may so say, will be equally drawn back towards the stone, for the distended rope, by the same endeavour to relax or unbend itself, will draw the horse as much towards the stone as it does the stone towards the horse, and will obstruct the progress of the one as much as it advances that of the other. If a body impinge upon another, and by its force change the motion of the other, that body also, because of the equality of the mutual pressure, will undergo an equal change in its own motion towards the contrary part. Changes made by these actions are equal, not in the velocities, but in the motion of the bodies. That is to say, if the bodies are not hindered by any other impediments. For because the motions are equally changed, the changes of the velocities made towards contrary parts are inversely proportional to the bodies. This law takes place also in attractions, as will be proved in the next scholium. Corollary 1. A body acted on by two forces simultaneously will describe the diagonal of a parallelogram in the same time as it would describe the sides by those forces separately. The explanation of that is, if a body in a given time by the force m impressed a part in the place A should with a uniform motion be carried from A to B, and by the force n impressed a part in the same position should be carried from A to C, let the parallelogram ABCD be completed, and by both forces acting together it will in the same time be carried in the diagonal from A to D, for since the force n acts in the direction of the line AC parallel to BD, this force, by the second law, will not at all alter the velocity generated by the other force m, by which the body is carried towards the line BD. So I should probably say this comes with a diagram of a parallelogram, whereby there is obviously a parallelogram, a square, the top horizontal line skewed to the left, and a diagonal line from the top left to the bottom right, and it's labelled A top left corner, B top right corner, C bottom left, D bottom right. So I guess I could say that again, just to, so if you've got that in mind. If a body in a given time by the force m impressed a part in the place A, so that's top left, should be with a uniform motion be carried from A to B, so that's top left to top right, and by the force N impressed apart in the same place should be carried from A to C, so that's top left to bottom left. Let the parallelogram ABCD be completed, and by both forces acting together, it will in the same time be carried in the diagonal from A to D, top left to bottom right. For since the force N acts in the direction of the line AC, top left to bottom left, parallel to BD, top right to bottom right, this force, by the second law, will not at all alter the velocity generated by the other force M, by which the body is carried towards the line BD, top right to bottom right. The body therefore will arrive at the line BD in the same time. It's the line top right to bottom right, whether the force N be impressed or not, and therefore at the end of that time it will be found somewhere in the line BD, same line. By the same argument, at the end of the same time it will be found somewhere in the line CD, and that's the bottom horizontal line. Therefore it will be found in the point D, the bottom right line, where both lines meet, but it will move in a right line from A to D by law 1. So that was a lot of describing just for a diagram. I think I will trust you to visualize these or look them up. Although the next one is even more complicated. Corollary 2, and hence is explained the composition of any one direct force AD out of any two oblique forces AC and CD, and on the contrary the resolution of any one force AD into two oblique forces AC and CD, which composition and resolution are abundantly confirmed from mechanics. As if the unequal radii OM and ON drawn from the centre O of any wheel should sustain the weights A and P by the chords MA and NP, and the forces of those weights to move the wheel were required through the centre O. You know what? This is impossible to follow. I will skip some of the corollaries where there's a diagram wherein it's impossible to understand just from listening to what I'm saying. Let's get to corollary 3. The quantity of a motion which is obtained by taking the sum of the motions directly towards the same parts and the difference of those that are directed to contrary parts suffers no change from the action of bodies among themselves. For action and its opposite reaction are equal by law 3, and therefore by law 2 they produce in the same motions equal changes towards opposite parts. Therefore, if the motions are directed towards the same parts, whatever is added to the motion of the preceding body will be subtracted from the motion of that which follows, so that the sum will be the same as before. If the bodies meet with contrary motions, there will be an equal deduction from the motions of both, and therefore the difference of the motions direct towards opposite parts will remain the same. Thus, if a spherical body A is 3 times greater than the spherical body B and has velocity 2, and B follows in the same direction with a velocity 10, then the motion of A is motion of B. Alright, motion of A to motion of B equals 6 to 10 in the ratio. Suppose then their motions to be of 6 parts and of 10 parts, and the sum will be 16 parts. Therefore, upon the meeting of the bodies, if A acquires 3, 4, or 5 parts of motion, B will lose as many, and therefore after reflection A will proceed with 9, 10, or 11 parts, and B with 7, 6, or 5 parts, the sum remaining always of 16 parts as before. If the body A acquire 9, 10, 11, or 12 parts of motion, and therefore after meeting proceed with 15, 16, 17, or 18 parts, the body B, losing so many parts as A has got, will either proceed with 1 part, having lost 9, or stop and remain at rest, as having lost its whole progressive motion of 10 parts. Or it will go back with 1 part, having not only lost its whole motion, but, if I may say so, 1 part more. Or it will go back with 2 parts, because a progressive motion of 12 parts is taken off, and so the sums of the conspiring motions, 15 plus 1, or 16 plus 0, and the difference of the contrary motions, 17 minus 1, or 18 minus 2, will always be equal to 16 parts, as they were before the meeting and reflection of the bodies. But the motions being known with which the bodies proceed after reflection, the velocity of each will be also known by taking the velocity after to the velocity before reflection, as the motion after is to the motion before, and is, as in the last case, where the motion of A before reflection, 6, as a ratio to motion of A after, 18, is the same as velocity of A before 2 to velocity of a after x, and that is 6 to 18 equals 2 to x, so x must equal 6. Got lost some of the florality because I was reading off maths rather than reading their nice linguistic, poetastic maths described in, essentially late Middle English? I don't know. No, not Middle English. I'm blathering. Okay, next paragraph. But if the bodies are either not spherical or moving in different right lines, impinge obliquely one upon the other, and their motions after reflection are required. In those cases, we are first to determine the position of the plane that touches the bodies in the point of impact, then the motion of each body, by corollary 2. Is to be resolved into two, one perpendicular to that plane and the other parallel to it. This done because the bodies act upon each other in the direction of a line perpendicular to this place. The parallel motions are to be retained the same after reflection as before, and to the perpendicular motions we are to assign equal changes towards the contrary parts, in such manner that the sum of the conspiring and the difference of the contrary motions may remain the same as before. From such kind of reflections sometimes arise also the circular motions of bodies about their own centres, but these are cases which I do not consider in what follows, and it would be too tedious to demonstrate every particular case that relates to this subject. Corollary 4. Here's the italics. The common centre of gravity of two or more bodies does not alter its state of motion or rest by the actions of the bodies among themselves, and therefore the common centre of gravity of all bodies acting upon each other, excluding external actions and impediments, is either at rest or moves uniformly in a right line. And now the explanation. For if two points proceed with a uniform motion in right lines, and their distance be divided in a given ratio, the dividing point will be either at rest or proceed uniformly in a right line. This is demonstrated hereafter in Lem 13 and Corollary, when the points are moved in the same plane. And by a like way of arguing, it may be demonstrated that the points are not moved in the same plane. Therefore, if any number of bodies move uniformly in right lines, the common centre of gravity of any two of them is either at rest or proceeds uniformly in a right line. Because the line which connects the centre of those two bodies so moving is divided at that common centre in a given ratio, in like manner the common centre of those two and that of a third body will be either at rest or move uniformly in a right line. Because at the centre of the distance between the common centre of the two bodies and the centre of this last is divided in a given ratio. In like manner, the common centre of these three and of a fourth body is either at rest or moves uniformly in a right line, because the distance between the common centre of the three bodies and the centre of the fourth is there also divided in a given ratio, and so on infinitum. Therefore, in a system of bodies where there is neither any mutual action among themselves or any foreign force impressed upon them from without, and which consequently moves uniformly in right lines, the common centre of gravity of them all is either at rest or moves uniformly forward in a right line. Moreover, in a system of two bodies acting upon each other, since the distance between their centres and the common centre of gravity at both are reciprocally as the bodies, the relative motions of these bodies, whether of approaching to or of receding from that centre, will be equal among themselves. Therefore, since the changes which happen to motions are equal and directed to contrary parts, the common centre of those bodies, by their mutual action between themselves, is neither accelerated nor retarded, nor suffers any change as to its state of motion or rest. But in a system of several bodies, because the common centre of gravity of any two acting upon each other suffers no change in its state by that action, and much less the common centre of gravity of the others by which that action does not intervene, but the distance between those two centres is divided by the common centre of gravity of all the bodies into parts inversely proportional to the total sums of those bodies whose centres they are, and therefore while those two centres retain their state of motion or rest, the common centre of all does also retain its state. It is manifest that the common centre of all never suffers any change in the state of its motion or rest from the actions of any two bodies between themselves. But in such a system, all the actions of the bodies among themselves either happen between two bodies or are composed of actions interchanged between some two bodies, and therefore they do never produce any alteration in the common centre of all as to its state of motion or rest. Wherefore, since that centre when the bodies do not act once upon each other, either is at rest or moves uniformly forwards in some right line, it will, notwithstanding the mutual actions of the bodies among themselves, always continue in its state, either of rest or of proceeding uniformly in a right line, unless it is forced out of this state by the action of some power impressed from without upon the whole system. And therefore the same law takes place in a system consisting of many bodies, as in one single body, with regard to their persevering in their state of motion or of rest. For the progressive motion, whether of one single body or of a whole system of bodies, is always to be estimated from the motion of the centre of gravity. And now we are on to Corollary 5, which goes: the motions of bodies included in a given space are the same among themselves, whether that space is at rest or moves uniformly forwards in a right line without any circular motion. And the explanation goes: for the differences of the motions tending towards the same parts and the sums of those that tend towards contrary parts are, at first, by supposition, in both cases the same, and it is from those sums and differences that the collisions and impulse do arise with which the bodies impinge one upon each other. Wherefore, by law 2, the effects of those collisions will be equal in both cases, and therefore the mutual motion of the bodies among themselves in the one case will remain equal to the motions of the body among themselves in the other. A clear proof of this we have from the experiment of a ship, where all motions happen after the same manner, whether the ship is at rest or is carried uniformly forwards in a right line. Corollary 6. If bodies move in any manner among themselves, are urged in the direction of parallel lines by equal accelerative forces, they will all continue to move among themselves after the same manner as if they had not been urged by these forces. Let me read that again because I think I emphasized it a bit incorrectly. If bodies, moved in any manner among themselves, are urged in the direction of parallel lines by equal accelerative forces, they will all continue to move among themselves after the same manner as if they had not been urged by those forces. And the explanation. For those forces acting equally with respect to the quantities of the bodies to be moved, and in the direction of parallel lines, will, by law 2, move all the bodies equally as to velocity, and therefore will never produce any change in the positions or motions of the body among themselves. Scholium. Hitherto I have laid down such principles as have been received by mathematicians and are confirmed by abundance of experiments. By the first two laws and the first two corollaries, Galileo discovered that the descent of bodies varied as the square of time, in duplicata ration temporis, in case you want to know the Latin for that, and that the motion of projectiles was in the curve of parabola, experience agreeing with both, unless so far as these motions are a little retarded by the resistance of the air. When a body is falling, the uniform force of its gravity, acting equally, impresses in equal intervals of time equal forces upon that body, and therefore generates equal velocities, and in the whole time impresses a whole force, and generates a whole velocity proportional to the time. Excuse me while I yawn. And the forces, described in proportional time, are as the product of the velocities and the times, that is, as the squares of the times. And when a body is thrown upwards, its uniform gravity impresses forces and reduces velocities proportional to the times, and the times of ascending to the greatest heights are as the velocities to be taken away, and those heights are as the product of the velocities and the times, or as the squares of the velocities. And if a body be projected in any direction, the motion arising from its projection is compounded with the motion arising from its gravity. Thus, if the body A, by its motion of projection, alone could describe in a given time the right lines AB, you know what, this is going to be difficult. I mean, scholarium presumably is scholarly mathematical demonstrations through diagrams. I'm going to just skip along past some of these bits that require diagrams. I mean, they're basically, one of them is a diagram describing the curved line of something being, a projectile. So it's a curved line going across a plane, and the other one appears to be an arc describing spherical bodies oscillating, probably cannonballs on a ship, knowing his other descriptions. Okay, let's get to... you know what, this is kind of waffly, I'll just do it anyway. Okay. So ABCD is a square, as you would imagine, top left, bottom right, and E is the line, this curved arc between A and D. Okay. If a body projected in any direction, the motion arising from its projection is compounded by the motion arising from its gravity. Thus, if the body A, by its motion of projection alone, could describe in a given time the right line AB, which is the horizontal top line of the square, and with its motion of falling along could describe in the same time the altitude AC, the vertical height of its fall, complete the parallelogram ABCD, and D is where it's landed, and the body that by that compounded motion will at the end of time be found in the place D. And there you go. And the curved line AED, which that body describes, will be a parabola, to which the right line AB will be a tangent at A, and whose ordinate BD will be as the square of the line AB. On the same laws and corollaries depend those things which have been demonstrated concerning the times of the vibration of pendulums, and are confirmed by the daily experiments of pendulum clocks. By the same, together with Law 3, Sir Christopher Wren, Dr. Wallace, and Dr. Huygens, Huygens, figure it out, the greatest geometers of our times, did severally determine the rules of the impact and reflection of hard bodies, and about the same time communicated their discoveries to the Royal Society, exactly agreeing upon themselves as to those rules. Dr. Wallace indeed was somewhat earlier in the publication, then followed Sir Christopher Wren, and lastly Mr. Huygens. But Sir Christopher Wren confirmed the truth of the thing before the Royal Society by the experiments on pendulums, which M. Marriott soon after thought fit to explain in a treatise entirely upon that subject. But to bring this experiment to an accurate agreement with the theory, we are to have due regard as well to the resistance of the air as to the elastic force of the concurring bodies. Let the spherical bodies A and B be suspended by the parallel and equal strings AC and BD from the centres C and D. About these centres, with those lengths as radii describing the semicircles EAF and GBH, bisected respectively by the radii CA and DB. Bring the body A to any point R of the arc EAF, and withdrawing the body B, let it go from hence. And after one oscillation, suppose it to return to the point V. Then RV will be the retardation arising from the resistance of the air. Of this RV, let ST be a fourth part situated in the middle, namely so that RS equals TV, and RS to TV is the ratio 3 to 2. Then will ST represent very nearly the retardation during the descent from S to A. Restore the body B to its place, and suppose the body A to be let fall from the point S. The velocity thereof in the place of reflection A, without sensible error, will be the same as if it had descended in vacuo from the point T. Presumably that means in a vacuum. Upon which account this velocity may be represented by the chord of the arc TA, for it is a proposition well known to geometers that the velocity of a pendulous body in the lowest point is as to the chord of the arc which it has prescribed in its descent. After reflection, suppose the body A comes to the place S, and the body B to the place K. Withdraw the body B and find the place V, from which the body A, being let go, should after one oscillation return to the place R. ST may be a fourth part of RV, so placed in the middle thereof as to leave RS equal to TV, and let the chord of the arc TA represent the velocity with the body A had in the Let the chord of the arc TA represent the velocity which the body A had in the place A immediately after reflection. For T will be the true and correct place to which the body A should have ascended if the resistance of the air had been taken off. In the same way, we are correct to place K to which the body B ascends by finding the place L to which it should have ascended in vacuo, and thus everything may be subjected to experiment in the same manner as if we were really placed in vacuo. These things being done, we are to take the product, if I may say so, of body A by the chord of the arc TA, which represents its velocity, that we may have its motion in the place A immediately before reflection, and then by the chord of the arc TA, that we may have its motion in the place A immediately after reflection. And so we are to take the product of the body B by the chord of the arc BL, that we may have the motion of the same immediately after reflection. And in like manner, when two bodies are let go together from different places, we are to find the motion of each, as well before as after reflection, and then we may compare the motion between themselves, and collect the effects of the reflection. Thus, trying the thing with pendulums of 10 feet in equal as well as equal bodies, and making the bodies to concur after a descent through large spaces as of 8, 12, or 16 feet, I found always, without an error of 3 inches, that when the bodies concurred together directly, equal changes towards the contrary parts were produced in their motions, and as of consequence that the bodies... Sorry, I got distracted by a wire moving on the floor. Not by itself. I found always, without an error of 3 inches, that when the bodies concurred together directly, equal changes towards the contrary parts were produced in their motions, and of consequence that the action and reaction were always equal, as if the body A impinged upon the body B at rest with 9 parts of motion, and, losing 7, proceeded after reflection with 2. The body B was carried backwards with those 7 parts. If the bodies concurred with contrary motions, A with 12 parts of motion and B with 6, then if A receded by 2, B receded with 8, namely with a deduction of 14 parts of motion on each side. For from the motion of A subtracting 12 parts, nothing will remain, but subtracting 2 parts more, a motion will be generated of 2 parts towards the contrary way, and so from the motion of the body B of 6 parts, subtracting 14 parts, a motion is generated of 8 parts towards the contrary way. But if the bodies were made both to move towards the same way, A, the swifter, with 14 parts of motion, B, the slower, with 5, and after reflecting, A went on with 5, B likewise went on with 14 parts, 9 parts being transferred from A to B. And so in other cases, by the meeting and collision of bodies, the quantity of motion obtained from the sum of the motions directed towards the same way, or from the difference of those that were directed towards contrary ways, was never changed. For the error of an inch or 2 in measuring may be easily ascribed to the difficulty of executing everything with accuracy. It was not easy to let go the 2 pendulums so exactly together that the bodies should impinge one upon the other in the lowermost place AB, nor to mark the places S and K to which the bodies ascended from after impact. Nay, and some errors too might have happened from the unequal density of the parts of the pendulous bodies themselves, and from the irregularity of the texture proceeding from other causes. But to prevent an objection that may perhaps be alleged against the rule, for the proof of which this experiment was made, as if this rule did not suppose that the bodies were either absolutely hard or at least perfectly elastic, whereas no such bodies are to be found in nature, I must add that the experiments we have been describing by no means depends upon the quality of hardness, to succeed as well in soft as in hard bodies. For if the rule is to be tried in bodies not perfectly hard, we are only to diminish the reflection in such a certain proportion as the quantity of the elastic force requires. For the theory of Wren and Huygens, bodies absolutely hard return one from another with the same velocity with which they meet. But this may be affirmed with more certainty of bodies perfectly elastic. In bodies imperfectly elastic, the velocity of the return is to be diminished together with the elastic force, because that force, except when the parts of bodies are bruised by their impact or suffer some such extension as happens under the strokes of a hammer, is, as far as I can perceive, certain and determined, and makes the bodies to return one from the other with a relative force, which is in a given ratio to that relative velocity with which they met. This I tried in balls of wood, made up tightly and strongly compressed, for first, by letting go the pendulous bodies and measuring their reflection, I determined the quantity of their elastic force, and then, according to this force, estimated the reflections that ought to happen in the other cases of impact. And with this computation, other experiments made afterwards did accordingly agree, the balls always receding one from the other with a relative velocity, which was to the relative velocity with which they met, as about 5 to 9. Balls of steel returning with almost the same velocity, those of cork with a velocity something less, but in balls of glass the proportion was as about 15 to 16. And thus the third law. So as far as it regards the percussions and reflections, is proved by a theory exactly agreeing with experience. In attractions, I briefly demonstrate the thing after this matter. Suppose an obstacle is interposed to hinder the meeting of any two bodies, A and B, attracting one the other. Then if either body, as A, is more attracted towards the other B, then that other body B is towards the first body A. The obstacle will be more strongly urged by the pressure of the body A than by the pressure of the body B, and therefore will not remain in equilibrium. But the stronger pressure will prevail, and will make the system of the two bodies, together with the obstacle, to move directly towards the parts on which B lies, and in free spaces, to go forwards infinitum, with a motion continually accelerated, which is absurd and contrary to the first law. For by the first law, the system ought to continue in its state of rest, or of moving uniformly forwards in a right line, and therefore the bodies must equally press the obstacle, and be equally attracted one by the other. I made the experiments on the lodestone and iron. If these placed apart, in proper vessels made to float by one another in standing water, neither of them will propel the other, but by being equally attracted, they will sustain each other's pressure, and rest at last in an equilibrium. Okay. This comes with a little diagram. We've got a circle with horizontal lines at the sort of vertically dissecting it. There's two of them. On, I'd say, the left first 10-20% of the circle, and on the right hand 10 to 20% of the circle. Presumably they are sections, so the left section is called F, or at least the side is called F, and the right side is called I, and the left line is depicted as E down to G, and the right line is I down to K. Or of going around the circumference E, F, G, and H, I, K, going down. Anyway, I'm sure the description will describe it better. So the gravitation between the Earth and its parts is mutual. Let the Earth Fi be cut by any place EG in two parts, EGF and EGI, and their weights one towards the other will be mutually equal. For if by another plane HK parallel to the former EG, the greater part EGI is cut into two parts, EGKH, or H, as I would usually say, and HKI, whereof HKI is equal to the parts EFG, first cut off, it is evident that the middle part, EGKH, will have no propension by its proper weight towards either side, but will hang, as it were, rest in an equilibrium between both. But the one extreme part, HKI, will, with its whole weight, bear upon and press the middle part towards the other extreme part, EGF, and therefore the force with which EGI, the sum of the parts HKI and EGKH, tends towards the third part, EGF, is equal to the weight of the parts HKI and is to the weight of the third part, EGF. Therefore the weights of the two parts, EGI and EGF, one towards the other, are equal, as I was to prove. Indeed, if those weights were not equal, the whole earth floating in the non-resisting ether would give way to the greater weight, and retiring from it would be carried off infinitum. And as those bodies are equipollent, EQUIPOLLENT, guessing equal or equipollent, in the impact of the reflection, whose velocities are inversely as their innate forces. So in the use of mechanic instruments, those agents are equipollent and mutually sustain each the contrary pressure of the other, whose velocities, estimated according to the determination of the forces, are inversely as the forces. So, those weights are of equal force to move the arms of a balance, which during the play of the balance are inversely as their velocities upwards and downwards. That is, if the ascent or descent is direct, those weights are of equal force, which are inversely as the distances of the points at which they are suspended from the axis of the balance. But if they are turned aside from their interposition of oblique planes or other obstacles, and made to ascend or descend obliquely, those bodies will be equipollent, which are inversely as the heights of their ascent and descent, taking according... Let me try that sentence again. I mean, that is we are talking a paragraph-sized sentence here. So, those weights are of equal force to move the arms of a balance, which during the play of the balance are inversely as their velocities upwards and downwards. That is, if the ascent or descent, is direct, those weights are of equal force, which are inversely as the distances of the points at which they are suspended from the axis of the balance. But if they are turned aside from the interposition of oblique planes or other obstacles, and made to ascend or descend obliquely, those bodies will be equipollent, which are inversely as the heights of their ascent and descent, taken according to the perpendicular, and that on account of the determination of gravity downwards. And, in like manner in the pulley, or in a combination of pulleys, the force of a hand drawing the rope directly, which is to the weight, whether ascending directly or obliquely, as the velocity of the perpendicular ascent of the weight to the velocity of the hand that draws the rope, will sustain the weight. In clocks and such like instruments, made up from a combination of wheels, the contrary forces that promote and impede the motion of wheels, if they are inversely as the velocities of the parts of the wheels on which they are impressed, will mutually sustain each other. The force of the screw to press a body is to the force of the hand that turns the handles by which it is moved, as the circular velocity of the handle in that part which it is impelled by the hand is to the progressive velocity of the screw towards the pressed body. The forces by which the wedge presses or drives the two parts of the wood it cleaves are to the force of the mallet upon the wedge as the progress of the wedge in the direction of the force impressed upon it by the mallet is to the velocity with which the part of the wood yielded to the wedge in the direction of lines perpendicular to the size of the wedge, and the like account is to be given of all machines. The power and use of machines consists only in this, that by diminishing the velocity we may augment the force, and the contrary, from whence in all sorts of proper machines we have the solution of this problem: to move a given weight with a given power, or with a given force to overcome any other given resistance. For if machines are so contrived that the velocities of the agent and resistance are inversely as their forces, the agent will just sustain the resistance, but with a greater disparity of velocity will overcome it. So that if the disparity of velocities is so great as to overcome all that resistance, which commonly arises either from the friction of contiguous bodies as they slide by one another, or from the cohesion of continuous bodies that are to be separated, or from the weights of bodies to be raised, the excess of the force remaining, after all those resistances are overcome, will produce an acceleration of motion proportional thereto, as well in the parts of the machine as in the resisting body. But to treat of mechanics is not my present business. I was aiming only to show by those examples the great extent and certainty of the third law of motion. For if we estimate the action of the agent from the product of its force and velocity, and likewise the reaction of the impediment of the product of the velocities in its several parts, and the forces of resistance arising from the friction, cohesion, weight, and acceleration of those parts, the action and reaction in the use of all sorts of machines will be found always equal to one another. And so far as the action is propagated by the intervening instruments, and at last impressed upon the resisted body, the ultimate action will be always contrary to the reaction. And then we come to Book 1, the motion of the bodies. Yes, I think I will stop there and save that for next time. That is all of the definitions done. It only took forever. Okey doke. Well, I will speak at you soon. Goodbye.